Hello, my name is Bob D. Hilster, and I am your particle model guru. Today I'm going to talk about the equation E equals mc squared, and in particular, fission. By the way, if you're new to the particle model, I suggest you watch these two videos. The particle model overview and levels of the universe will give you a better understanding of some of the things that I say during the videos. I do not always try to cover everything in one short video, so watch these. It'll be a big help for you. Okay, so when you look up E equals mc squared in the Wikipedia, you find that it brings you to an article titled Mass Energy Equivalence. And it quotes, in physics, mass energy equivalence states that anything having mass has an equivalent amount of energy and vice versa, with these fundamental quantities directly relating to one another by Albert Einstein's famous formula E equals mc squared. Anything having mass has an equivalent amount of energy, and vice versa, anything having energy has an equivalent amount of mass. Well, a little bit of background. I found this article from Scientific American published August 24th in 2015. And this is an excerpt from that. According to scientific folklore, Albert Einstein formulated his equation in 1905, and in the single blow explained how energy can be released in stars and nuclear explosions. Energy can be released. This is a vast oversimplification. Einstein was neither the first person to consider the equivalence of mass and energy, nor did he actually prove it. There were others who had worked on the same idea. From this same Scientific American article, it stated, extended bodies have produced numerous and prolonged headaches in special relativity. This equation, basically by Einstein, comes from special relativity. But such as the fact that the mass of the classical electron also comes out to m equals 4/3 E, the energy, divided by c squared. Or if you rewrite it, you'll get the equation energy equals 3/4 mass times c squared. It's different than what we see very often. Maybe not so much different, but it's certainly going to give you different values. That is, using relativistically correct mathematics, one gets a result that at first blush contradicts the answer everyone expects and loves. Arguments of how to properly resolve the issue persist to this day. So it has a problem. It needs more work, as I usually like to say. So let's talk about fission. This is a link to a video that describes fission. And in particular, people use the U-235 atom. It's generally stated to be slightly unstable. So if you could take a neutron, which is over here, and you can shoot it at a U-235 atom, they say that it temporarily becomes U-236, which is even more unstable. Apparently only exists for a very short period of time, whereupon it breaks up into 2 separate atoms and 3 neutrons. And in the process, it releases energy. Whatever this is, there's energy there. But the process of doing this. Now, this energy is generally called the nuclear binding force. But what I see here is that the particles are conserved. Another screen from that video shows this, that the neutron hits the U-235, it splits, but it splits in, and this is one of the ways it splits. It apparently can do it in different ways. This is barium-141. This is krypton-92. There's the energy. This slide didn't show the 3 neutrons, but here you can see that the 1 neutron, 1 plus the U-235 makes 236, and then that sets up the U-236, which they say is unstable, breaks into these 2 pieces plus 3 neutrons. And the particles are conserved. You know, at first blush, if the particles are conserved, what's this? Where's this energy coming from if all the particles are still there? Well, so the final explanation, this is nothing more than an expansion of the first one, adding 2 more, where you get a chain reaction in this, that one splitting gives another splitting and another splitting, and releases this binding energy. It's not clear at all what the binding energy is. In fact, I heard recently at a conference that they're considering the fact that there isn't a binding energy, and don't have any background on that or where that's coming from. But one might ask, you know, normally we talk about energy, we talk about mechanical energy, electrical energy, magnetic energy, and so on. But most of these talk about the binding energy as the energy being used, generated. And so the video concludes, the amount of energy produced by this reaction is described by Einstein's equation. Now, so finally the equation gets into the picture, and they're going to, you can calculate, if you will, using how much energy is there, how much, where all this came from. And that this energy is used to generate electricity or to explode an atomic bomb. That's what the video says. It's the energy coming from this splitting of the atom that generates electricity. Okay, so this is just a brief review of a nuclear reactor. What you have here are, you got U-235 in here, and you can hardly see it. Tiny little particles shown there, probably moving around. You got 2 control rods which control the rate of the reaction so that it doesn't get out of hand. And the energy heats the water. The hot water comes over here to a container that's sealed, and as the water gets hotter and hotter, it creates steam. The steam pressure turns the turbine, and the turbine turns the generator, and the generator makes electricity. It's this energy, it's the energy that heats the water. Now, I generally am asking the question, how does energy heat the water? What's the mechanism going on? How, but it's never explained. Is it binding energy? Is it the other energy? How does it heat the water? Never explained. You're supposed to just accept the idea that energy can heat water and ultimately through a nuclear power plant generate electricity. I've stated this before, maybe not in this context, but the particle model states that moving particles can heat water. Water heats up when the water molecules vibrate at a faster rate. Even with ice, which is obviously to us not hot, the atoms, the molecules of water are vibrating, although very slowly. You bring heat close to the or you bring the ice out of the freezer, put it on the table or in a glass and set it there, the the air around it has atoms that are vibrating faster, and it's the interaction of the faster moving atoms in the air that causes the atoms in the ice to move faster and finally melt. I'm going to use my hands here if I can. When it's ice, it's just barely vibrating. As it heats up, the molecule atoms tend to fly over or go past each other, getting to a state of water. So you go from ice to water, you make it hotter, these molecules can escape, and when they escape, because they're moving so fast, vibrating so fast, you get water vapor. That's the process I've described any number of times. Particle model states that moving particles can heat the water. Particles can do that. So my conclusion that the fission processes that causes U-235, 36 to split, and the resulting atoms, barium and krypton, and neutrons gain speed as they split apart. You literally mechanically knock them and split them apart. It's a mechanical process, and in the process, these are moving, and it's these moving particles that move through the water and heat up the water. Next time I'm going to talk about another video, but this time we're going to use E equals mc squared to actually do a calculation. And it's going to be calculated using E equals mc squared. So these videos, even the one I just talked about, they're trying to say that E equals mc squared is part of what really helps explain how nuclear reactors work and the atomic bomb work in the process of releasing energy, and the energy heats the water. And in this video, I suggest you watch it. It's interesting. I will cover it next time and see how this particular E equals mc squared actually is validated by this calculation. My name is Bob D. Hilster, and I am your particle model guru. Tune in next time when I'll explain more of the universe using the particle model. Thank you for your attention.